Okay, here's my solution for the problem that we did on Friday of week 2. So we did a problem with a uniform sphere that has charge distributed throughout its volume, and that charge was plus Q. And then we had a spherical shell that we said was a conductor, and we're going to put a minus 2Q on the conducting shell. So the question asked, find the electric field as a function of R, the radius from the center of the distribution for all values of R. And what we decided is that there were 4 regimes. So there is the R, so we called these 3 radii, R1, R2, and R3. So we said for R greater than R3, we're going to use Gauss's law. The net flux of the electric field through a closed surface is equal to the charge enclosed by that surface divided by epsilon naught. Okay, so we'll do that, and I'll write down Gauss's law again. E dot PA is Q divided by epsilon naught. So if I put my imaginary surface out here, my imaginary sphere, my Gaussian sphere, then I have E at that point times the area, 4 pi r squared, is equal to the charge enclosed. The charge enclosed is just Q minus 2Q divided by epsilon naught. And so the field is equal to 1 over 4 pi epsilon naught r squared times negative Q. I just add them together, so this is inward attractive. Okay, for R greater than R2, but less than R3, that was in a conductor. And we said that the electric field inside a conductor has to be 0. By the way, that means by Gauss's law, there must be a minus Q on the inner surface to make the Q enclosed be 0. Okay, there we go. So what about for R greater than R1, but less than R2, the space in between? Again, we do E dot dA is Q enclosed over epsilon naught, E 4 pi r squared, and now the Q enclosed is just the inner over epsilon naught. And so we get that the electric field is equal to 1 over 4 pi epsilon naught times Q outward. And the last instance, well, this is a little bit harder. So when R is less than R1, now, and I'm going to sort of zoom in here and draw what's going on, I have this ball of charge, but I'm wondering what the field is at some distance, little r, that's inside the uniform sphere of charge on an insulator. And I've told you that it's uniformly distributed. You have to know that. But that means that I just want a fraction of what's in there. So again, I would start with Gauss's law, and I would write E times 4 pi r squared. Like I said in class, you will never forget the area of a sphere after this class. This time, though, it's a little bit more complicated. Let's call it a charge density times the volume inside my Gaussian sphere divided by epsilon naught. So I can cancel out the 4 pi's here, but I need to know rho. So I know, though, that I can always calculate a density by taking the total charge and dividing it by the total volume. The total volume of the thing that's got that charge on it, right? Okay, so I put that in, and I'll cancel out these r squareds, and I'm going to solve then that E is equal to Q over 4/3 pi r1 cubed, that's rho, times 1/3 r, so the 3's will cancel, divided by epsilon naught, and what I get is Q over 4 pi r1 cubed times just r. So what's interesting about this is it's just linear in r, but that makes sense, right? So we check when little r is equal to r1, then the electric field is just Q over 4 pi, ooh, I lost my epsilon naught, 4 pi epsilon naught r1 squared. That makes sense, right? I mean, that's just Coulomb's law for a sphere of radius when you're at the edge of the sphere. So that totally makes sense. Should I do r greater than r1? No, because don't forget up here, right? We've already defined that this is only true for r less than r1, so it's not relevant to consider that. What you should note, though, is that when r equals 0, then the electric field is 0. That's a good thing, though, right? Because what way would it be pointing at r equals 0? So in fact, what we have is, as a function of r, right, we have an electric field that increases linearly, and then decreases as 1 over r squared, right, until it gets to a certain point, jumps down to 0, and then jumps up and has a negative, or jumps down, I should say, and has a negative value after that. So it's an interesting problem, very interesting problem. Okay, I'll stop there. Okay, I won't stop there. I just saw I had a mistake. I lost my r squared over here. Okay, so there we go. Now it looks just like it should. Coulomb's law.